went through the Summation Convention last week, and I want to start this week by reviewing what we said last week. The review is going to be for emphasis for those who understand and to help those who did not fully understand, because there is no reason in this world why everybody in the class cannot understand. The thing is not, the thing can become tedious eventually, but it is as you are taking one single step at a time, you will find out that you are in a position to know, you are in a position to understand, and you are in a position to follow. So we get back to the Summation Convention. So we'll meet this week one echoes linear. In week one, we talked about magnitude and directional vectors, linear independence. We talked about basis. I've talked about how a basis set can be orthonormal, like the one you are used to, but why it does not have to be orthonormal. And then we introduced several terms. We talked about several things. We talked about the area of a parallelogram. We talked about direction. We talked about area of a rectangle, linear independence, basis set of vectors, magnitude, components of a vector, normalized, condition for basis, orthogonal, dimensions of space. And you know that the dimensionality of space is related to the number of vectors that can be linearly independent. If you don't know linear independence, you cannot understand the dimensionality of space. We talked about autonomous set. Then we talked about, I think we talked about projection. I'm not so sure, but if we haven't done that, we will talk about that later on. I'm not sure we talked about spanning of a space, but we talked about scalar. You know what scalars are. You know what vectors are now. And we talked about a scalar product, which you knew before. Multiplication by a scalar, you already know. We talked about vector product. And then we saw that there is a relationship between the scalar triple product and linear independence and the dimensionality of space. If you have a three-dimensional space, you span it with a set of vectors. If you take the scalar triple product of those vectors, if it gives you 0, that shows you that the vectors are not linearly independent. Then we talked about the vector, where I don't think we talked about the vector triple product, but you know that from previous work. And scaling of a vector you are familiar with. Then the volume of a parallel pipette, that is what I talked about, which is related to the fact that these vectors on it are linearly independent. We didn't talk about the volume of a tetrahedron, but I hope we'll get to that today. We talked about area of a rectangle, area of a parallelogram, and then we now try to introduce the fact that if you can break a vector into components I, j, k, the vector itself is the vector sum of the component of the coefficient of on I times I, the coefficient on B times B, and the coefficient on J times beta, then times J, the coefficient of K times K. So if you have that, that is what you have been used to. The above representation for any three-dimensional vector is instinctive in us. We'll be using it. We usually assume the Cartesian autonomous basis sets I, J, K. Simply renaming I, J, and K, E1, E2, and E3, we proceed to write the same representation as A1, E1, plus A2, E2, plus A3, E3. Here now, E1 is playing the role of I, E2 is playing the role of J, E3 is playing the role of K, but with the advantage that if we are to have more vectors, we are just going to increase the number of the E's, which is not, you don't need to look for new symbols. And again, our A, you just the number of subscripts it will have. So that reduces the number of things we have to keep track of. And we can write the sum in the normal standard form that we have here, whereby F is the sum from I is equal to 1 to 3 of AI, EI, where AI ranges from 1 to 3. So we explained why using E's instead of I, J, and K is better, that it helps us with parsimony. And then the parsimony is achieved by indexing. And the example on page 9, where we move from 3 to 10 dimensions really shows us that it would have had a lot of problem. If we now go to 30 dimensions, when you don't have, you have only 26 letters in the alphabet, then you have to do all sort of funny things. The kind of funny things they do on Excel. You know, in Excel, this talk of column 1, 2, column A, B, C, D, E, F. By the time you get to Z, then you now start A, B, A, C, and all. We would have had to be doing those kind of things. I think the Excel people should better just talk of A1, A2, A3, and then you can now have as many columns as possible without going into all that kind of arrangement. But that's for them to do. Now we go to slide 10 here, where we now we have some equations that we can write like this, and to show the flexibility of standard summation, and then we can write it compactly with the summation sign here. And then we now move to the Einstein summation convention. The convention has a very simple rule, which looks easy. Learn it as it looks. The logic is always consistent. But the things can become complicated fast. And it was so fast that even last week, a student asked a question which confused me also. And it was only when I go home that I saw that what I did was right after all. Then I sent the solution to the class. But that shows you how easily anybody can get confused. So it's not, if you get confused, you are not alone. Even your lecturer too can get confused. So there's nothing to worry about there. When you are confused, go back to the simple rules again. It will tell you the way out. Don't just go back to the simple rules. That is what everybody would do. Points to note. Summation convention. There is no change to your equation. It only helps you to express the same idea in a more compact form. You will eventually see how a single term can replace 9 terms, can even replace 27 terms, can replace 81 terms, and you will see how simple it is. We move in steps of 3 raised to power. When we have 0 order is 1 term. 1 order, which is a vector, is 3 terms. Second order, which is a tensor, is 9 terms. Third order, which is the third order tensor, is 27 terms, and so on. You will see how these numbers build up as we go. The rule is simple. Make sure there is never a time when any index is repeated more than once. Only allow an index to be repeated when such a repetition implies a summation over all the possible values, but make sure it never occurs more than once. So instead of writing a summation sign, just make sure that the index you want to sum over has been repeated in each term. When it's like that, it will always work. If you are going to do summation over another time, you have to use a new dummy index so that you will not repeat an index more than once. So that is the rule. Anytime you have repeated an index more than once, there is an error. But if it has to happen, then you must go back to your summation sign. When you are using your summation sign, you don't have to worry about how many times an index is repeated. But when you are using the summation convention, the repetition of an index more than once is an error. If you look now on the equation on slide 8, the equation on slide 8, let us go back to slide 8. This is slide 8. The equation on slide 8, which is this last equation, F is equal to A1 E1 plus A2 E2 plus A3 E3, which is the summation from I is equal to 1 to 3 AI EI. It can now be written as F is equal to AI EI. We don't need the summation sign again. The summation over the index I is disposable as the simple fact that the index is repeated over I is equal to 1, 2, and 3. Summation over I can be taken for granted. A repeating index such as this one is called a dummy index for the simple fact that it can be replaced by any other index that takes values over the same domain. So it could have been AJEJ, it could have been AKEK, it could have been A alpha, E alpha, it can be anything. But just that they are repeated and we are summing them over the same number. They are all the ways we have written them above are equivalent. Similarly, if we go to the equation on slide 11, where we wrote yi is equal to the sum, let us go back to slide 11 and see it there. In slide 11, we had this summation compactness where we're summing over j, yi is equal to aij xj. You look at this, you see that in this case we are summing over the j's. So when you come back to our current slide, what we see here is that yi is equal to aij xj, and I goes from 1 to 3. J will also go from 1 to 3, but it is the sum here. Again, the repetition of J shows that the summation sign over J is disposable as the simple fact that the same index is repeated over J is equal to 1 to 3. Summation over J can be taken for granted. But one other thing I want you to see in this equation is the fact that the other index that is not repeated in each term, that is I here, shows you how many equations you have. So when y is 1, that is one equation. When y is 2, that's another equation. When I is 1 is one equation, I is 2 is another equation, and I is 3 will be another equation. So you can see here the dummy indices indicate summation. The free indices will tell you the number of equations you have. In this particular case, we have only one free index. And because there is only one free index, that means that there are this number of summation. There are 3 equations involved in the situation we have found ourselves. So that is what you can get from there. And again, as before, a repeating index can be replaced by any other index that takes values over the same domain. Consequently, yi is equal to aij xj is equal to aik sk is equal to ai alpha x alpha, provided it is known that j, k, and alpha each take the values over 1 to 3. Note that I is not repeated in any term. Such an index is called a free index, and like I've told you, the free index determines how many equations we really have. When the free index takes a value, that's one equation. When it takes another value, that's another equation. When it takes a third value, that's still another equation. So if a single free index will give you 3 equations, 2 free indices we also see gives you 9 equations, and 3 free indices will give you 27 equations. 4 free indices will give you 81 equations. And you can see this, that when there is 0 free index, there is no free index at all, you have 3 to the power 0 equations. 3 to the power 0 is 1. So when it is 1, it is 3 to the power 1 is 3. When it is 2, it's 3 to the power 2 is 9. When it is 3, it's 3 to the power 3 is 27. When it is 4, it's 3 to the power 4 is 81. When it is 5, it is 3 to the power 5. I don't even know what 3 to the power 5 is, but you can calculate that and you know it. So telltale signs. A trained eye sees almost instinctively when there is an error in an index object following the summation convention. Here are the things you look for. A free index must occur once only, and nothing but once in each term of an equation. A free index must occur once, and it must always occur once, and only once, and nothing but once in each term in an equation. It must occur in each term. But if a free index is missing in a term, there's an error. A dummy index must occur twice, but it does not have to occur in another term, because wherever it occurs shows that that particular term you are saying is a summation among all the possible values. So, but it does not have to occur on any other term. So just be watching out and be keeping track of these issues. The products and terms. We must be very careful what we mean by a term. So you can see, we checked this last week, and I decided to attack something that looked very simple to me, but it turns out to be controversial, because at the end of the day, one student challenged it, and by the time she challenged it, we worked it out, and I just said, let us not waste our time in the class because I wasn't getting it right in class. And I promised you I will give it to you after the class. Please notice that in this class, you can use the chat room. I will visit the chat room once in a while, and it is quite possible that what I see in the chat room is something I will respond to. And even if I don't respond, our experience is that the lecturers who attend, some lecturers attend this class, so some of them may decide to respond to the question, and then some of your own classmates may also decide to respond. And I encourage that. If while the lecture is going on, somebody is having difficulty and he posted something on the chat room, I encourage other students to look at it. If you understand it, answer him, and that you will learn something. Even if your answer is wrong, it will be corrected eventually by me or by the other lecturers that are present online. Okay, now because this last one caused us problem last week, I don't know whether you all got the solution that I gave, which is this. You can decide to expand first on the J term. If you expand first on the J index, you will see that it is only this term that has J. So if you expand first on J, it's only this term that will change. So Zi remains Zi and Bi remains Bi. But the terms that have J will have to be summed over all the possible values. So you have there AI1x1 plus AI2x2 plus AI3x3, whereby we have exhausted all the possible expansion values of J. Then when we now want to expand on I also is a dummy index because for every term there are two values. For every term there are two values. So if you start this first one, you see that it will be Z1 into A11x1, A12x2, A13x3, and so on. The others will follow the same kind of pattern, which you can now write like this. And you will get the same result by using the summation convention directly. The young lady who thought there should be a three, that this thing occurs three times, there is nothing like that. This is how this thing comes out now. Now, what we are going to do, the question is, if we can expand first on J, could we also have expanded first on I? Could we? The answer is yes, we could have expanded first on I, and that is what I will show you in the next slide. In this slide, I decided to expand first on the I index. If we expand first on the I index, each term now will be a summation in J. So the first time I takes the value of 1, we have this summation with Z having the value of 1 and with I having the value of 1. Everywhere I occurs, you see 1, 1 there. But J is still quiet because we have not yet opened it up. When I takes the value of 2, J is still quiet again, but you have Z2 here, A2 here, B2 here, because all the values of Y has changed to, all the values of I has changed to 2. Similarly, in the third case, you have that all the values of I has changed to 3, and you have this term. Now, if you open each one now by expanding along J, you have exactly the same expression we had before. Exactly the same expression we had before. Because when J is 1 now, and when you expand this in J, you see Z1, AI1x1 plus AI2x2 plus AI3x3 and plus B1, which doesn't change, and so on. And you get explicitly exactly what we had before. So that was the challenge of last week. And again, if this causes you a problem, please post that question on the chat room. I will see it, and I may be able to either answer you during the class, or you get an email or something, some posting on the website that you can see and you can understand the answer straight away. Okay, so let us now see how we can interpret expressions. Now, suppose you have a matrix, and the matrix is A11, A12, A13, A21, A22, A23. Let me see whether I have that matrix anywhere. Let's see, because it will be good, instead of just repeating it for you, if we have the matrix somewhere. Don't know whether I have written a matrix somewhere before. No, that was an error on my part. But you can write out the matrix in the indices. So what we are saying is that if you multiply, yes, this is it. This is the matrix. So if you have these two matrices, A11, A12, A13, A21, A22, A23, A31, A32, A33, if you have these two matrices and you are trying to multiply them, and you get the product will be B11, B12, and so on, the product of these two matrices. How can you write this in index form? To know how to write it in index form, you have to just take a look at what we have here. I am saying that the product will be Aij, Ajk. If it is the product of A is equal to B. So now you do it in another way. But if you just expand Aij, Ajk, when I is 1 and K is 1, because I and K are free indices. So the first expression, like we said before, there will be 9 expressions here because there are 2 free indices. I is a free index, K is a free index. If you take, by the time I takes all its possible values and K takes all its possible values, you are going to get 9 expressions. So the first expression, you are going to sum over J. In the second expression, you are going to sum over J. In the third expression, you are going to sum over J. And so on. You are always summing over J. But I and K are free indices, so they take specific values in each expression. That if you now do the multiplication of those two matrices the way you know how to do it, you will discover that the expressions you get for B11 is this same expression. The expression you get for B12 is this same expression. The expression you get for B13 is this same expression. Therefore, we conclude that when you are multiplying two matrices A is equal to B, this is the expression that gives you the product. It is Aij, Ajk. You are multiplying the same matrix by itself. Now, what I want you to do is that I want you to go into the chat room and tell me if we multiply A by A transpose. Not that instead of multiplying A by A, we multiply A by A transpose. I want you to show me that the product you will get, it should be Aij, Akj. That is AA transpose is Aij, Akj, whereas AA itself is Aij, Ajk. So try and work that out. If you understand this, you should be able to do that. I'll give you 2 minutes to try that out. That is, you take A and you multiply it not by A itself, by the transposition of A. And I will say this formula will no longer work. The formula that will work will be Aij, Akj. I want you to confirm that, because working this out in longhand will help you to have the confidence that the expressions you are using are correct. So try and work this out. I'll give you 2 minutes. And if you agree with that, you say so on the chat room. If you don't agree, say so and tell us what you got. It should be Aij, Akj. You have 1 more minute to confirm that when we multiply A by its transpose, the answer we get is the same thing as Aij, Akj. Now we have spent 2 minutes, so I will look at your answers when I have the time. But it can be seen that the correct interpretation of the previous slide by the summation convention rule exactly matches the product of the matrices above. This must be worked out. This must be worked out. This must be worked out manually to get a good feel for it. It does not come naturally. Come on, don't be lazy. Transposing the right matrix in the product leads to Aij, Akj, which I've asked you to do. And that is what I asked you to do. And if you didn't finish it, try and finish it on your own, and you'll be able to understand it. Now, so there are consequences of the summation convention. Because of the summation convention, there are 2 very important constructs that come about. The first one is called the chronicle delta. It's also called the substitution symbol. We will see a more important interpretation after defining tensors. And the second thing is the Levi-Civita 3-index symbol. also called the alternating symbol. Again, a more complete understanding of what it is awaits a formal definition of a tensor. But right now, we're going to take these two things as if they're just index constructs. They're just some things that have indices, and they have specific interpretation depending on the way the indices are arranged. So it is how the indices look that determine the interpretation of these things. So let us begin. Once you understand the summation convention, the next important thing is to understand what the canonical delta is. And then you will see that the canonical delta is related to the Levi-Civita 3-index symbol, which we will define shortly. The canonical delta is defined by the following 9 equations. Delta 1, is equal to 1. Delta 1, is equal to 0. Delta 1, is equal to 0. Delta 2, is equal to 0. Delta 2, is equal to 1. Delta 2, is equal to 0. Delta 3, is equal to 0. Delta 3, is equal to 0. Delta 3, is equal to 1. You will observe that anytime this thing has explicit indices that are equal, the answer is 1. The value is 1. When they have explicit indices that are not equal, the answer is 0. So by the index notation, we can write this simply as a single indexed equation. We can say delta ij is equal to 1 if I is equal to j, and it is equal to 0 otherwise. That is, if I is not equal to j. There is no dummy index here. There is no summation because I and j are not the same. There is no summation. But if you now make I and j to be the same, then there is a summation, and we still have to go again and interpret. But right now, we have not, the 2 indices it has are free. Because there are 2 free indices, this equation becomes 9. You remember that when there are 2 free indices, you have 9 equations, like you have seen here now. If there are 2 free indices, there are 9 equations. If there are 3 free indices, there are 27 equations. If there are 3 free indices, because that is 3 raised to power 3. That is 3 times 3 times 3. And you will see that when we get to the Levi-Civita symbol, there will be 3 free indices, and therefore there can be many more equations than we have here. The canonical delta is operationally known as the substitution symbol. Here is the reason why. Consider the arbitrary Cartesian base vectors EI and EJ. They are arbitrary. You will call them like I or J or I or K or I, K or I. Where we have not committed to the values of the indices, we will take, the indices we take, except for the fact that each index will take 1 or 2 or 3. So EI can be E1, can be E2, can be E3. EJ can be E1, can be E2, can be E3. So what we are saying is that EI here can be I, J, or K of your old way of thinking. And EJ also could be I, J, or K. It could be any of them. So it is therefore correct to write EI.EJ is delta IJ, because this dot product will give us 1 only if I and J are taking the same values. For example, if I is 1 and J is 1, we are going to have 1. If I is 2 and J is 2, we are going to have 1. If I is 3 and J is 3, we are going to have 1. In any other situation, we are going to have 0. For instance, you know that the dot product of the base vectors will only give you 1 if you are talking about the same base vector. Otherwise, I.k is 0, I.j is 0, j.j is 1, k.k is 1, and I.I is 1, and so on. So that is what, but all those equations, all those expressions are already contained in this simple expression here. So you can see how powerful the canonical delta is. Many things that would have been Benujoing, just be talking in a very simple compact equation. You have expressed all the relationships that can possibly exist between the base indices in a single equation like this. That's the power of the chronicle delta. The chronicle delta is operationally known as the substitution symbol. Here is why. Consider the arbitrary Cartesian base vectors EI and EJ, where we have not committed to the values and so on. It is correct to write this. We know that already. Now, if you want to express a vector V in terms of its components, how can you know what the V's are? Okay, how can you know what the components are? Let us take a dot product of V with one of the vectors, with one of the base vectors, which we have not determined. So we use EJ, because EJ represents all the base vectors, because J can be 1, J can be 2, J can be 3. So when J is 1, that is your old I vector. When J is 2, that's your old J vector. When J is 3 here, that's your old K vector. So when we say EJ here, we mean it can be any of the others. Now, if we write it this way, we can see that V dot EJ, because we have already assumed that V is V1 E1 plus V2 E2 plus V3 E3. When we do not even know what V1, V2, and V3 are, we are just saying let V1, V2, and V3 be its coefficients in the E1, E2, and E3 directions. Now, if you take a dot product of V as defined here with EJ, you have this. But you remember that EI dot EJ is delta IJ. We've said that before. So you now have that V dot EJ is V1 delta 1J plus V2 delta 2J plus V3 delta 3J, in which case we have already allowed the summation that is implicit in the repetition of I to take effect here. So this equation and this equation are the same. So we now examine the values of both sides for different values of J, because in this expression here, what type of index is J? Can you go to the chat room and tell me what type of index is J in this expression here? Is J here a dummy index or a free index? Please go to the chat room and tell us what J is. Is it a free index or a dummy index? Okay, I'm not able to see the chat room, but I will take a look at it during the break time. Okay, so you should see that what we have here is that J here is a free index. It's not a dummy index. So we can now, because it's a free index, there will be 3 equations. So we can take the first equation when J is equal to 1. We have V dot E1 is equal to V1. When J is equal to 2, V dot E2 is equal to V2. When J is equal to 3, V dot E3 is equal to V3. We can therefore summarize what we have here and say that, and write that, let me just, and write that VIEI dot EJ is equal to VI delta IJ is equal to VJ. But if you look at what happened in the last expression, the last equality, you will see that what simply happened is that because there is an index that the delta has, it substitutes it with for the one that V does not have. That is how the chronicle delta behaves. If you like, you can always go through this long expression to find out it is true, or you can just understand that it's always true, and you come here and you see it that it is true. So that is what you can get from here. It is true whenever you want to use your dummy, whenever you want to use the chronicle delta, it substitutes the other symbol. So the last expression shows the way the substitution works. Whenever the chronicle delta shares an index with any other variable in the same expression, left-hand side, chronicle delta shares the index I. Take out the shared index, that is, remove I from V, and replace the removed index with the remaining symbol J. Remove the chronicle delta, you obtain the result on the right-hand side. It is those simple steps. Those steps are so simple as we are looking at them one by one, but when you now look at them on the whole, you will see that it's not simple as it has a far-reaching effect. Observe the following, that following the above steps gives the expected result of the previous slide. So that is what gives us this equation that Vij delta Ij is simply equal to Vj. You can see that the previous slide, slide 26, indeed, as we have it here, proves that expression to be true. So we have here in slide 28, we have other expressions that will help you to see the substitution power of the chronicle delta. So in this S alpha B delta I alpha, the shear symbol is alpha. So alpha goes away, and the I that is remaining, that gives you now Si beta, with the chronicle delta disappearing. Similarly, here, the shared symbol is, the shared index is J. So you see that alpha is going to replace J there. And you can now see that the result is Ti alpha K with J gone and the chronicle delta gone. Again, even when the chronicle delta operates on itself, one of them must vanish. So you can use whichever one you choose to vanish, the result you get at the end will be the same. Let us say we want the one on the right hand side to vanish. We want the one on the right hand side to vanish. The share symbol is J, so it will now be J here will be substituted by alpha. You have delta I alpha. Similarly, if you want the one on the left hand side to vanish, J is the common symbol, is a common symbol here. It should now become delta, because J will vanish, it now become delta alpha I. Now, we write delta I alpha here. It turns out that the substitution symbol is symmetric. That is, it is the same value no matter where its indices appear. It's not all the things we are going to look at that are symmetric. It just turns out that the chronicle delta is a symmetric symbol. We can prove it, but let us just leave it as that now. Similarly, if you have delta Ij, you can choose whichever, both of them are, both symbols are shared. So you choose one. If you choose one, you either have, depending on what you choose, you either have the answer to be delta II or delta Jj. They mean exactly the same thing, because if it's delta II, it means that I takes all the values it can take. That is delta 1, 1, delta 2, 2, delta 3, 3 added together. If it's Jj, the same thing, because J goes from 1 to 3, and the answer will be 3. Similarly here, you see that Eijk, delta Jk, either J or K, you can use either J or K as the substitution symbol, and it will give you either Eijj or Eikk. And Eijj or Eikk are exactly the same thing. So you get the same value. If we are happy with that, we will soon take a break. We will take a break in 5 minutes time. And before we go on break, I want to at least introduce the other symbol. When we introduce the other symbol, we go on break, and then by the time you go on break, I think I shall have had time to look at all the comments on the chat room, so that if there are things that are problematic, I can take a look at them. So what we have here now is on slide 29. We are introducing the Levi-Civita 3-index symbol. It's a good idea to practice the chronicle delta to mastery before trying to understand the next symbol. Once you are good at the former, the latter is very easy. But if you are not good in the chronicle delta and you are now trying to understand the Levi-Civita, it's going to be a very hard day for you. So make sure you fully understand the chronicle delta, the way it functions, the way it operates, and then you can now come and understand the Levi-Civita symbol, the Levi-Civita 3-index symbol. We can define it in terms of the chronicle delta. There are several ways of defining it. We can define it in terms of as a determinant containing only chronicle delta. Delta 1i, delta 1j, delta 1k, delta 2i, delta 2j, delta 2k, delta 3i, delta 3j, delta 3k gives you that the result of that determinant is what we mean by Eijk. That Eijk has 3 symbols, and it behaves in a very funny way that you will see, and very funny and important way. For instance, let us allow I to be 1, J to be 2, and K to be 3. In such a case, we have E123 is equal to delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. When we remember that when the explicit indices of the delta are not equal, the values become 0. So you see that we have 1, 0, 0, 0, 1, 0, 0, 0, 1. In this case, I am not talking about how many times you eat your breakfast or you eat your lunch or you eat your supper. Because anytime I'm telling students 100, they think I'm saying they eat only breakfast. When I say 010, they eat only lunch, and 001, they eat only supper. That's not what we are saying here. We are saying that the Levi-Civita 3 index symbol will give you the values 100, 010, 001, as you can see. And if there's anybody in the class that is not obvious to, please let me know in the chat room or ask your friends, because immediately you can see that it gives you the identity matrix, and the determinant of the identity matrix is simply 1. You can get the determinant, expand anywhere you like. The answer is 1. So E123 is equal to 1. You can get all the other values. You can, for instance, let I be 2, let J be 1, and let K be 3. If you do that, you will discover that if you do that kind of thing, you will have some interesting changes in this thing, and it will give you other values. So it is this is the way that the 3 index symbol works. Okay, so let us go to the next slide. So we can see that if you substitute the appropriate values, you will see that E123, E321, E312, they are always equal to 1. And E132, 321, and 213 will give you -1. And all other cases, especially E111, E112, E113, where any 2 are equal, no matter which 2, you are going to get 0. So there are 27 of them, and out of the 27 of them, only 6 are not trivial. The others are trivially 0. The 6 that are not trivial are cyclic and anticyclic permutations. You can see that E123, E231, and E312 are cyclic arrangements of 1, 2, and 3. But E132 are anticyclic arrangements of 1, 2, and 3. So when you have a cyclic arrangement, you get 1. When you have an anticyclic arrangement, you get -1. But you don't need to take that. You can just go back to the original definition. If you go to the original definition, you will see that from the original definition, you can always substitute I to be 2, J to be 1, and K to be 3 to get E213. And you will see that the determinant you are going to get is going to give you a negative number. So that is how it is. So there is no hide and seek in this thing. You don't need to take my word for it. You can always prove to yourself. And I encourage you to prove all these things to yourself. Don't say the lecturer said that. No, doesn't matter whether the lecturer said that. Do you know it to be true on your own? And the way you know it to be true, if you want to try E321, let I be 3, J2, and K1. And you will see that the determinant you are going to handle at the end of the day is going to become -1. You can try it out, and you should try it out. In fact, you should try the entire 27 out and make sure that all the values that are going to get, like I told you, you will get 1 for these 3 cases, you get -1 for these 3 cases, and for the remaining 21 cases, you are going to get 0. When something that is defined like that is called the Levi-Civita 3 index symbol, and it is defined in terms of the chronicle deltas. Returning to 0. Okay. Using the fact that the transposition does not alter the value of the determinant, we have an equivalent definition. We can have ERST is equal to delta R1, delta R2, delta R3, delta S1, delta S2, delta S3, delta T1, delta T2, delta T3. So it doesn't matter. It's the same definition, but all that happens is that we can transpose a determinant and it is still the same value of the determinant you will get. Even if the matrices are different matrices, their determinants are the same. Okay, so by the definitions we have made of the two alternating symbols, we can now get the product of them. If we do the product, the first time will be when we do the first row of the first determinant with the first column of the second determinant, and you see that you have delta R1, delta R1, delta 1I, delta R2, delta 2I, delta R3, delta 3I, which when you have it like this, you have delta R1, delta I1, 1I, delta R2, delta 2I, delta R3, delta 3I. If you look at it, you will see that this is the summation over a particular value from 1 to 3. So you can easily write this as delta, you can see delta R, you can see delta R alpha alpha I, which will give you all of this. And that is the same thing as delta Ri because of the substitution nature of this delta symbol. There's one line okay, so the second one will be delta R alpha, delta alpha J, delta R alpha, delta alpha K. It could be beta, it could be under anything. It could be K. No, it cannot be K. It could be alpha and sigma and anything you can use instead of alpha here. But if you do that, if you write it explicitly like this, you will see that it's a sum like this. You can see that this type of sum is the same as this type of sum. If you look at it carefully, you work this out and make sure you are happy with every step of the way. So if you do that, let us see how do we get delta Rj here. You can see that if you have delta R alpha, delta alpha J, the substitution nature of delta I alpha J will make this delta Rj. Similarly, this one will be delta Rk. So ERST, EIJK is simply delta Ri, delta Rj, delta Rk. So you see that when you now have the deltas, you see Rs and T are RST, 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 and the Ij and K. So the RST are coming column wise, whereas the Ij and K are coming row wise. IJK, 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 and no two are the same. If you look at from the expression here to this, following these steps, this is very easy to remember. This product is the most complicated product you will deal with in the index symbols, but it's very, very instructive and profitable to work it through so that this doesn't come as a shock to you, because we are going to do several things with this now. What we will do after now is that we are going to let two of its indices be equal. When the two of its indices are equal, you see what then will come out. And then after some time, we let four indices where two pairs of two indices are equal, and you see what comes out. But if all the indices are equal, you also see what that becomes. Clearly, not forgetting that repetition of an unknown index signifies a summation, we can write that ERSK, that is EIJK, is what we have here. So if we have, what we have done here is that we have taken this previous something here. Instead of having ERST, we said ERSK. So we changed it. If we change the T here to K, we must change every occurrence of T in the expression to K. So that's what we have done in this expression here. So everywhere T occurs, we make it K. So here, instead of T here is K, instead of T here is K, instead of T here is K. And you will see that when we write out this corner piece here, delta KK is written as delta 1, 1, delta 2, 2, delta 3, 3, in which case there is a summation implied. There is nothing like that in any of the others. And delta 1, 1 is 1, delta 2, 2 is 1, delta 3, 3 is 1. When you add the 3 together, you get 3. So that is the That when you allow the last indices to be equal, this is what you get. Now we can expand. I hope everybody here remembers how to expand a 3 by 3 matrix determinant. If you want to expand, you can expand using the third row. It is easier to expand using the third row or the third column. You can, if you do that, you have this. So it's delta ki into this determinant minus delta kj into this determinant plus 3 into this determinant. If you do that, you remember that there are 2 by 2 matrices determinants now, which are easy to work out. The first one here is delta rj times delta sk minus delta sj times delta rk. And then you have minus delta kj here, which is delta ri times delta sk minus delta si times delta rk. And then 3 into this. If you open the bracket and you have all of these things, and by the time you work them out, please work them out quietly, coolly, and don't rush. If you rush at this point, you will miss very important things. If you don't rush, you will have the confidence that you will know this. So at the end of the day, see the expression we have. We have delta Ri delta Sj minus delta Sj delta Rj. You see, Ri, so you the first two deltas are taking the Risj, and the second one is Sirj. So in the first case, you do them in an orderly fashion. In the other case, you swap them, and that brings the minus. That is what you have here. So there is a very mechanical trick to go from, even though we can get from here to here by working it out, but we can get straight from here to here by observing the arrangement of these symbols. So suppose instead of just one index, there are two indices that are equal. So instead of this being RST, we have RJK, and IJK here. So all you need to do is to just substitute where you had S before now, put J there, and you have this. And when you have this, what we are doing is that if S here becomes J, so everywhere that's S there, you have J instead of S. So you have Ri delta JJ and then Ji delta Rj. So that's what I am talking about there. So with the delta JJ, this delta JJ will give you 3. And in this delta JIRJ, you use the substitution nature of the delta, you get this. And it gives you 2 delta Ri. So again, you can see it's related to what you have here. The delta is simply R. The two indices that are free here are the ones that remain. So delta Ri, and it is 2 of it that you have here. So you see what we are examining here. We start from the most complex situation where you have 6 indices, 3 for each of the E's, and you have this complicated determinant. From this determinant, you can obtain all the other results of when 2 of the indices are equal or when 2 pairs of the indices are equal. So that is what you can get from here. And the question you may then ask me is that what happens if all the indices are equal? If R becomes I, what do you then have? I want you to go to the chat room and tell me what you have if R becomes I. I'll give you a minute. Suppose that if R becomes I, that means that you have EIJK times EIJK. EIJK. What will be the result? So go to the chat room and tell me the result. If R and I are equal, so that is that. What is EIJK from here? I will go to the chat room to see your answers there now. I know how to get to the chat room. So 11:20. Well, I can see Aibo Teso Joseph. Your answer is wrong. Awujale Olasubomi, your answer is wrong. What are the others awake or asleep? What happens when R becomes I in that last expression? Caleb, your answer is wrong. Itunu, your answer is wrong. Victory, wrong answer. I'm still waiting for the others. Is this class sleeping? Yes, Patrick Oloko. Patrick Oloko, correct. Yes, some people are woken up now. So I hope you are not just guessing. You know precisely why this is so. Those of you who had the wrong answers, I hope, please, I want to see whether people like Awoyale, Igbo Teso, Caleb Alikwe, and Itunu, I want you to tell me if you now understand what the correct answer is. If you can, if it is still a problem, I want to know. I want to know from those who got the wrong answers before. Olashubomi said, I don't understand how. Okay. I don't understand how. Okay. So let's see if I can explain how for the people who don't understand how. Because some people are not following this at all. Okay, those people who don't understand, you can see that if we have explained that ERJK times EIJK is equal to 2 delta RI, if you turn R here to I, then on this other side, you must turn this R here to I. So that means that EIJK is equal to 2 delta II. And you remember that delta II is delta 1, 1 plus delta 2, 2 plus delta 3, 3. So delta II itself is 3. So this expression now becomes 2 times 3. So that is how you get the answer. So I want to go back to the chat room now and see whether the people who didn't understand. Okay, Flourish, good. Thank you, Flourish. Flourish has explained just as I got it. So, I just got, okay. So the person who didn't understand it now understands it. Okay, you understand it better. So you can see that you have to work this thing out. If you just look, if you just keep looking, you cannot understand. But if you work it out. Similarly, if there's anybody who didn't understand what we did before, you will see that that is exactly the same thing. And you can see that Flourish May, I'm sure can help you out because she has a very clear understanding of what's going on there. So, and then there may be other people who are just shy, who are not saying anything. But I don't want you to be shy. Come on, tell me if you understand. Tell me if you don't understand, because if I know you don't understand, then I will spend a little bit of time and explain it, and that may be the difference. Because you can see now, some people are thinking it is one, some people are thinking it's two, some people are thinking it's three, whereas the correct answer is six. Some others are not even trying, and that is very discouraging. I want you to try. Try, even if you are wrong, then we will get a correction, and then you know it, and then all of us will be happy together. Okay, because like I said, there is nothing I'm telling you that everybody cannot understand. There's nothing, absolutely nothing. So let us continue with our slideshow from current slide. Okay, so that is how it is. And to get uh, that is how we have been proceeding from the previous one. So if you understand this, now wind backwards, you will see that each of the other things that we did before should be understandable. Okay, so let us now, with what we have done, we are now able to do, there are certain things we can now do. There are certain things we can now do. We are going to go back and first of all revisit the products you know. You knew about the dot product and the cross product. We are going to express both of them now using this new technology we have. We now have some important ways of expressing stuff. For instance, remember, I hope you remember that ei.ej is equal to delta ij. That we've said that over and over. If you do not remember this, go back to the notes. You see that we have expressed it over and over. If that is the case, if a dot b, let us you have a vector a and a vector b, you can write vector a as aieI, that is a1e1 plus a2e2 plus a3e3. Similarly, vector b is a b1e1 plus b2e2 plus b3e3. Who can tell me why we didn't make this one biei? Go back to the chat room and tell me why when I wrote this as aiei, why didn't I write this one as biei? Go to the chat room and tell me why did I do it like that? Why did I use J? I'm in the chat room now, waiting to I will answer your question, Flourish me later. Okay, I just want to clarify what we are solving for is the number of terms, not actually writing out equations. No, we are writing out the equations. We are not solving for the number of terms. We are writing what you have on the left-hand side means. That's what we are saying. I hope you got my question. My question is, if I have A dot B, I say it is equal to AI EI times BJ EJ. Why didn't I say it is AI EI times BI EI? Why didn't I write it like that? And I want you to go to the chat room and tell me why I didn't say B is BI EI. First of all, is my question clear? Because we are not answering, it could be that the question is not clear. If you understand the question, fine. Yes, there are two separate vectors here, but why can't I explain that? Why can't I? Because B itself is E1 is B1 E1 plus B2 E2 plus B3 E3. So that's what it is. But why didn't I? It would have been correct to say it is BIEI. But why did I not use it? Why did I not say BIEI? Why did I say BJEJ? Yes, Daniel Sadiq. Daniel Sadiq already understands it. So, because I could have written BIEI, but if I did that, my dummy index will now be occurring 4 times. You remember that we cannot allow a dummy index to repeat more than once. A dummy index cannot appear more than twice. Because I'm not getting enough answers from the class. So this is what I'm going to do. I'm going to go back again and bring out the, what I'm saying here is that why didn't I, okay, instead of this, okay, what to do now? Slide. So the question I'm asking the class, why did I not write it like this? Why is it wrong to write it like this? Why must I not use I here since I've used it here? So that's what I'm asking. I'm asking the class. I'm asking people to go to the chat room and explain or and tell me why this is not equal to this, but it is equal to this. Whereas BIEI is still B1E1 plus B2E2 plus B3E3. Why is it that despite the fact that BIEI is equal to B1E1 plus B2E2 plus B3E3, which is the same thing as the value of the vector B, why can we not write it like that here in this dot product? That is the thing that I'm still waiting for enough people to respond to, and that's why I'm still in the chat room. And I want people to respond in your own words so that we know what you think, and then that will help me to know whether I should move on or I'm just talking to myself. Ola Oluwalayomi Saba said something which is not correct, but I think you have now. Yes, Oluwalayomi Saba has got it right now, and then Sadiq got it right. David Akinola, one of the rules you gave us is that the dummy index I cannot be repeated more than once. So that is the rule. He said I gave you. Okay, so I'm the lawgiver. Okay, fine. But at least just say one of the rules is that it's not me giving you. I didn't invent that rule. An index can't appear more than twice in summation. It doesn't align with the summation convention rule. We cannot have repeat dummy index more than 2 times to avoid writing the index twice. So you can see, yes, I think generally the class, please, those who are not responding, Aha, let me tell you something that you may not know. Better know this. There are 5 marks that are going to be given to you for participation. Let me tell you how we arrive at the 5 marks. We are going to take all the chat register. We are going to analyze it against your name. And if you do not respond up to 10 times in the entire term, you are going to get a very low grade out of that 5. So the response is not necessarily correct. We are not insisting that you must, but the response shows your participation. As long as you are not saying something stupid. There are people that will now start advertising something they want to sell or saying something really stupid. You are going to be penalized if you waste our time by saying something stupid. But the responses you are giving me, for instance, the people who are already on their way now, Flourish May is on her way to collect the 5 points. She hasn't collected those 5 points. She's already answered, she already commented up to 3 times in today's lecture alone. So, whereas some of you have not even said one thing since the beginning, you are on your way to getting 0/5 in that assessment. There is an assessment on your class participation, and the assessment of your class participation is going to be based on your performance in the chat room. And your performance in the chat room is not on how many questions you answered correctly, but how much participation we got from you in the chat room, because that feedback is necessary for us to teach you well. If you do not have feedbacks, we will not be able to teach you properly. We will be saying things that we do not need to say, and we'll be avoiding things that we need to explain so that you can understand. So I am going to go back to the slideshow now. And but before I go back, let me just see if there's any new question or any new query or anything that you want me to address. Nobody. Last person that talked is the Wood testimony. And most of the comments I've got, virtually everything apart from the first few ones, have been correct. The index, an index cannot appear more than twice in a term. So let's see whether we can move on. Time is moving so fast here. Where is the... So you can see why this is the way it is. So here we now write that we can now write that we cannot, because we can take the scalars that are here can go. It is only the vectors that we cannot just, the vectors, once there's a dot product, we must look at that dot product. You remember that ei.ej is delta ij. So you have ei.ej is delta ij. And if you remember the substitution symbol, so that delta ij, you can either substitute I for B for j here or j for I here. Whichever one you do is correct, because it's only one delta. Once you use it up, you have used it up. So it is either AIBI or AJBJ, whichever one you arrive at, will still give you A1B1 plus A2B2 plus A3B3. You can see that suddenly, just by writing things in the index notation, we prove the theorem that A dot B is just the sum of the products of the respective coefficients. Straight away, that is what A dot B is. And you will see that if you understand how to use these symbols, if you know how to use them, you will see that it is always, many of the things that are serious theorems will just become transparent. Note on the second line how we avoided having 4 indices of the same type by invoking the fact that a dummy index is mutable. When you have an index that is mutable, if it has already been used twice in an expression, you do not use it again in that expression. That is it. Because all this will become an expression because there's a product sign in them. You remember that anything that is joined by a product is still the same expression. So let us move on. Okay, so we are now going to We're not going to do something that's a little bit more complicated than that. We're going to go into the vector product. The vector product. Recall that from your previous work, you know that E1 cross E2 is E3. And if you don't know, you know that it is E1 cross E2 is the magnitude of E1 times the magnitude of E2 times the angle between them. And I think this what I'm telling you here is something that should be proved. So let me just duplicate this slide and prove it instead of just telling you, because you will just say, but you said. Let's duplicate this slide. Okay, since we duplicated the slide, I'm going to modify this. I'm going to take this table off. Okay. Okay, so what is E1 cross E2? It is the magnitude of E1 times the magnitude of E2 times the sine of the angle between them, 90. Okay, so let us look at this now in the slideshow. So slideshow from current slide. Okay, what I am saying here is this: if the cross product, you remember that E1 is your old vector I, and E2 is your old vector J. What is E1 cross E2? E1 cross E2 is the magnitude of E1 times the magnitude of E2. These are unit vectors. They are orthonormal. And what is the angle between E1 and E2? Is 90 degrees in the direction of is in the direction of E3. So let me just finish doing that. So for the elementary definition of the cross product, we know that what we have here, E1 cross E2 is the magnitude of E1 times the magnitude of E2 times sine 90, because between the X and Y directions, the angle between them is 90 degrees. So I want you to write for me on your chat room. You will say, put the value here, times put the value here, times put the value here, and just prove to me that this expression is E3. What is it? You remember that the cross product of two vectors is the magnitude of the one vector times the magnitude of the second vector, sine of the angle between them, in the direction perpendicular to both of them. The direction perpendicular to E1 and E2 is E3, what is the z-axis. So you have E1 times magnitude of E1 times magnitude of E2. So what is the magnitude of E1? What is the magnitude of E2? What is the sine of 90? So put this, and let me see you in the chat room. I'm in the chat room now waiting for you. Yes, somebody says it's 1 times 1 sine 90. What is sine 90? You have not told us what sine 90 is. Aha. So it is what it is 1 times 1 times 1 E3. Okay. 1 times 1 times 1. That's what we got. So because many of we are any assertion we are making, we are not just making that assertion. We are actually working it out from your previous knowledge. Because some people will just say, that's what the teacher said. So okay. So you find it, you are finding you can follow this thing. You can see, you can follow it. There is nothing I am saying that is not based on what you already should know. Good. I'm happy with that response. So you can see it is in a similar way. It's a similar way that E2 cross E3 will be E1. And E3 cross E1, all you need to do is to ask yourself, what is the magnitude of E2? What's the magnitude of E3? And what is the direction perpendicular to both of them? What is here now? What is the magnitude of E3? What's the magnitude of E1? And what is the direction perpendicular to both of them? And you will see that all these expressions here are coming from those facts. There's nothing, we are not jumping any gun. The expressions are coming from those facts. Okay, so if clear, we can now go back to what I was doing before. So let us say we want to say EI cross EJ, no matter what I or J would mean. Okay, so we want to say, okay, if I is 1 and J is 3, it will be 1 times 1 sine 90 in the direction of -2. Because in the right angle rule, you remember the right angle rule you used to do for your cross product, it will be minus E2, that is the angle, that is the direction now, not E2, when it is 1 and 3. So, but if you use this expression, EIJK, the small e, that is the Einstein, that is the Levi-Civita symbol, EK. If you write this out, it will be E131 E1, E132 E2, E133 E3. And this is 0, this is 0, and the only thing that's not 0 is E132. Go back again and see that anytime the indices are repeated in this E's, you have 0. So it is only E132, and E132 is -1. If you've forgotten, let me take you to where we said it. If you forgot, you need to come back to this point. You can see that E132, E321, E213, you can see these are 1, these are -1, and the others are zeros. So we are referring to what we have already done before. So if you forgot that, you move back and see it. So you have to be going back to that page to see this. So we can say let I be 1, J2, let I be 2, J3, let I be 3, J1. All the possible combinations are here. With all those possible combinations, we will see that EI cross EJ, if we compare it to EI, JK, EK, we find out that the answers are always the same. So it is for that reason that I'm able to write for you here that EI is equal to EJ. So I'm able to write for you that EI cross EJ is EI, JK, EK. Why? Because look at all the possible values of I and J. K is dummy, so it doesn't matter. Look at all the possible values of I and J. You see that what you have in this column is always the same as what you have in this column. Therefore, this expression and this expression are the same, which is what I am emphasizing here. From that point on, after using this table to prove it, if you now have any two arbitrary vectors, you have AI, EI cross BJ, EJ, take all the scalars out of it, AI, BJ out there. What you have left is EI cross EJ. You can now write EI cross EJ from this formula that EI cross EJ, instead of EI cross EJ, we just say EI, JK, EK. So this is now, this expression now is the expression for the cross product of two. This is the expression now for the cross product among those two vectors. Let's see whether this is the expression for the cross product of those two vectors. Slideshow from current slide. So how do we get the expression for A cross B? We first of all establish that EI cross EJ is EI, JK, EK. And if that is the case, A cross B will become EI, JK, AI, BJ, EK. Please, everybody go to the chat room and tell me the nature of each of the, in this last expression, you tell me the nature of the index I, the nature of the index J, the nature of index K. At each one of them, take them one by one. Is I free or dummy? Is J free or dummy? Or is K free or dummy? That's question one. And once you have answered that question, I'm going to follow it with another question. Is I free or dummy? Is J free or dummy? And is K free or dummy? Take them one by one. Is I free or dummy? Is J free or dummy? Is K? Yes, fight with me. I can see your answer. Okay. 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 So generally, you have. Now, the second question is, how many equations do we have there? How many equations do we have in that expression? How many equations is it? How many equations do we have? Patrick Oloko said just one. Oloko, please answer me. Did I pronounce your name correctly? Oloko. Okay, good. Okay, so Patrick Oloko said there are, so that's just one equation. Okay, now the next, since Oloko has said it's only one equation, the Wood testimony has also said it's only one equation. Those of you who have not yet answered me, I want to give you another question. Why? How did you get only one equation? How did you know that it's only one equation? You remember that there are a number of free indices. Okay, how many free indices are there? 0. The number of free indices is 0. And how do you use that to calculate the number of equations? It's 3 to power 0. The number of equations you are dealing with is 3 raised to power the number of free indices. What is 3 to power 0? 3 to power 0 is what? 3 to power 0, because there are 0 free indices, and the number of equations will be 3 to power 0, which is equal to 1. If there is one free index, how many equations do you have? If there is one free index, there will be 3 equations. Thank you, David. If there is one free equation, you have one free index, you have three equations. If there are two free indices, how many equations do you have? How many expressions do you have? 9. If there are 3 free indices, how many expressions do you have? There are 3 free indices, 27. So you can see the logic. You can see that this I'm going. Thanks for the responses. Very, very good responses. And your responses are not good just because you are getting it right. Even if you don't get it right, you give me an opportunity to tell you the right thing, to correct you. So, but if you don't say anything, you don't even give me an opportunity to help you. And if you don't give me an opportunity to help you, I will penalize you for that, because you should give me an opportunity to assist you. Okay, so you can see now why A cross B is equal to EIJK, AIBJ, EK. So you need to expand this. If you now expand this quantity, you will see that all the cross product formula you are having, they are hiding inside that expression. I don't want to go into the. We are now at the point of defining the dyad. What I want you to do is to now write out. Let me go back. You agree with me that there is only one equation, but there will be, if there are 3 triple summations, so there will be 27 terms in that. 27 terms. So expand this and get all the 27 terms. This A cross B, expand it, get all the 27 terms, and then go back to this page. Let's see what the page is now. Yes, go back to page 31. You use the value of E1, 2, 3, 3, 2, 1, and all the other values, and you use it to put it there so that you can see that in this expression, it may look messy, but you will see that those 27 expressions end up giving you your cross product expression correctly, because most of them will be zero. Remember that out of the 27, how many of them will be zeros? Out of the 27 something, how many of them will be zeros? I'm going back to the chat room. How many of the 27 will be zero? There will be 21 zero, and the ones that will not be zero will be just 9. That's the one that will not be. Sorry, will be just 6. There will be only 6 that are not zero. So just work that out, and you'll see that you have from there the expression for cross product. 3, good, marvelous. You are marvelous. 6 non-trivial. The remaining are trivial. Okay. So the remaining are trivial. We will stop the lecture here today, and I will send this particular. We've made some modifications in the slides. By later in the day, till tomorrow, the slides that I actually used in this, as well as the audio and video, will be on the website by tomorrow latest. So it is now for you to go, and you can take the slides, because that may give you better referencing. And then the audio, for those who did not follow or who are not in class, if you have friends that didn't come, so you can help them to go and you can tell them to go and download and listen. Like I said, I do not tell you, I do not insist you must come, but if you don't come, you are not free to not do the homework. You're going to get 0 if you don't do the homework. So have a nice day, and thank you for your attention. Bye-bye.